All right, in this video, we're going to take a look at a two-dimensional trajectory problem where we are fired at an angle. We're going to take a look at two cases. We're going to look at when we land at the same height and when it lands at a different height. Again, we're going to look at the Navy railgun with its speed of 3,000 meters per second. This time we are elevating it to 60 degrees. So I am going to take my projectile here. It is going to make an arc. This is 60 degrees. The original speed is 3,000 meters per second. From here to here is my range. Now the very first thing I'm going to do is, because I'm at an angle, is I'm going to split this into x and y coordinates. So I need to know an x and a y velocity. So 3,000 cosine of 60 is going to be my velocity in the x direction. So that is 1,500 meters per second. And my velocity in the y direction is going to be 3,000 sine of 60. So that's going to be a much uglier number, 2,598 meters per second. Once I have this, this problem is handled the same way a horizontal launch is. I'm going to do my x coordinates, or I'm going to do my y first, and I'm going to do x over here. Y first, because we know the downwards acceleration, we can find some things out a little easier. So, need to find the range if it lands at the same height. So looking at this guy here, we have YO equals 0, YF equals 0. I could put 23 and 23. As a matter of fact, let's do that. Why not? Just so you guys can see what that'll do. Lands at the same height that it was fired from. My velocity original in the y is 2598. My velocity final in the y is negative 2598. Symmetry. If it's going up this speed at the beginning, at the same spot on the other side, it's going to be a reverse. The acceleration is negative 9.8 meters per second squared. Time we don't know. So if I want to find the range, I need to find the time it is in the air. This piece right here is an extra piece of information because we are landing at the same height. We can use the quadratic, which we've done before, and solve for time. Or this time, I'm going to go at it with VF equals AT plus VO, because I happen to know this one this time. So I need to get to negative 2598 with an acceleration of negative 9.8 over some time t, and I start at 2,598. This equation is more straightforward than the quadratic, so this is why I'm preferring it this time. 2598 minus 2598 is 5,196 negative 9.8 times t. So I get a time of 530 seconds is equal to time. This thing is in the air for a long time. It's in the air for over 8 minutes. I'm going really fast, and we're ignoring air, so that messes with all sorts of things. Once I have this, let's go to the x coordinates. XO is going to be 0. XF is what I'm looking for. My original speed in the x direction is, had it over here, 1,500. My final speed in the x direction is 1,500. The acceleration is 0. That's why I know these are the same. There's no acceleration horizontally. These two numbers will be different. The time is the same. It is the 530 seconds. So we know that xf equals 1/2 at squared plus v naught t plus xo. That 0, that 0. So xf equals 1500 times 530, or a very, very far distance of 795,000 meters. Railguns are awesome. Now, if we want to find the range if it lands on the ocean, this trick isn't going to work. So we're going to try a second approach. We are going to keep the same y coordinates. YO equals 23, but YF equals 0. We know that V naught Y was 2598. VFY we don't know anymore because we are not at the same height. Acceleration still negative 9.8. Time we don't know. So to solve it out this way, I'm going to show you the quadratic approach, which we could have used on the other one, but you'll see why we didn't. So xf equals 1/2 at squared plus v naught t plus x naught. We're dealing with y's, so let's make sure and I change these and label them to y's. And then let's put them in here. I end on the ground, 1/2 of 9.8. So 1/2 negative 9.8 t squared plus v naught. That is a big number, 2598t, plus we started 23 meters above the ground. So 0 equals negative 4.9 t squared plus 2,598t plus 23. I can't solve this for t very easily. This isn't a 0, so it's harder than the horizontal launch problem. I have no clever ways of coming around it, so I'm just going to use the quadratic formula. This is my A term, my B term, and my C term. So time, my x variable, is equal to negative b plus or minus the square root b squared minus 4ac over 2a. And I'm going to chug them in here. So t is equal to negative 2598 plus or minus the square root of 2598 squared minus 4 times negative 4.9 times 23. This is going to be very, very big for 2a. So that is 2 times 4.9 negative. Get some big ugly numbers here. Negative 2598 plus or minus the square root of 2598 squared of 67,49604 minus 4 times 4.9 times 23 minus that's a whopping 450.8. Great. Divided by negative 9.8. So doing this one, 67,49604 minus 450.8. I get negative 259.8 plus or minus 297.9 divided by negative 9.8. You can see at this angle here, these are almost the exact same numbers because this doesn't really matter with an absurdly high speed. So this is going to get me is going to get me a total time of roughly 530.2 seconds. Just what we got on the other side. 23 meters in this huge distance doesn't really matter that much. So this time is almost the same. So then we'd go to our x coordinates, punch in the time, and be done.